Okay, just for completeness, so you can fully understand everything in chemistry, I'm just going to add entropy to this. This is not in your syllabus, and neither is the next one, Gibbs, but it will help you understand a lot of things, so it's going to be quite useful. So, to be honest, you actually know these things already. So, heat transfer, you know that it goes from hot to cold, and so that's telling you that heat dissipates, and so enthalpy favors the negative delta H. This other one, entropy, you also know this as well. You should probably know it as diffusion and things that go from random to increased randomness. So when you look at something like this one's a great example because you have increased the potential energy and you've also increased the order. So if you saw this on the moon, you wouldn't think twice about saying that something intelligent has done this, but yet you have a cell that has infinite complexity and order and buildup of chemical bonds, but you don't seem to think that that is unusual. So let's just move on. Entropy is the total amount of distribution, so it's the randomness. We're looking for a positive value, and we end up looking like this, and this is far less probable. So if you see this situation here, if you rearrange, don't move those dots, but rearrange them, it's highly unlikely that all the order will be on one side and the other side. It's far more likely to be an infinite number of other different ways. And so the data booklet here is the physicists who actually work out this, give us a value of randomness. You can see here that obviously steam, the water is in a gas state, so it's going to have a larger randomness to it. And I'll leave the rest just for your perusal. We're doing Gibbs next video. And so the main things here is you can see from this graph that entropy doesn't increase a lot by increasing temperature as it does with states. And as you expect, liquids and gases are actually, sorry, liquids and solids are quite close to each other. Intermolecular forces work quite well. But once you get to these huge spaces here where the distances are too great for intermolecular forces to have an effect, of course, you have this much greater increase in entropy. So states are far more important than temperature, and gases are far more important than the other states. Okay, so that's important just to realize that when you're wondering why something is happening. Okay, and so here's a good example just to appreciate how it works. So here you're going from which is a decrease. Well, you've got one particle solid plus one particle gas, so that's definitely not a decrease. You've got two particles gas. One was a gas, one was a solid, so that's obviously not that's a decrease as well. Two particles of gas going to three particles of gas, that's not increasing. This one here, you've got three gases, three particles of gas going to two particles of liquid. So decreasing particles and state. So that's definitely decreasing in entropy. Same with this one. This one's a little bit more tricky. Which has the greatest increase? Which ones have increases? This is two gases to two gases. Um, and so that's definitely not a clear increase. It looks like it's the same. Solid plus gas to just one solid, that's a massive decrease. Here we've got three gases to a less, a lower state, a different state that's less random. So that's a massive decrease as well. This one here, you've got one solid, two liquids going to just one solid and one gas. So they're both a solid, and then you've got two liquids compared to one gas. And so that one is actually an increase because the two liquids are very much like a solid, even though there's two of them. They are next to each other, and these are zipping around in space. So it's definitely C